Okay. Just going to wait for some people to come in, if possible, or I might just get started right away. You know what? I might just get started right away. All right. So welcome back to STEM Online Academy. Okay. My name is Jason Masterakos. And for those of you who know me, I am the head of the channel where we specialize in advanced mathematics and physics by teaching a unique way of problem solving, which requires strengthening your visual spatial skills and problem solving skills. Okay, so what we're going to do today is we're going to be looking at special functions that you've probably haven't seen before. Okay, and those special functions are known as the error function. Okay, the exponential integral function. And the other function that you probably haven't heard of is called the Fresnel function. Okay, and you're going to see why these integrals are important from my book, Advanced Integration Techniques. Okay, it's because, first off, these are integrals that you haven't learned in elementary calculus. Okay, they're advanced integrals. All right, so let's get to it. All right, so let's start sharing the screen. Okay, let's go to, so I'm going to share the screen just 1 second. Here. And we're going to go directly to the whiteboard. All right, sorry for that, that's not there yet. All right, so it's a live show today, right? So we're going to look at special function problem solving and the error function, Fresnel integrals, and etc. Okay, so today's menu, we're going to start off with special functions, why they exist. Okay, number 2 is going to be the error function and Gaussian symmetry. I'm going to get into that. I'm going to give you background on it. If you have any questions, you can ask me along the way. Number 3 will be a little bit on probability and heat, the heat equation. Okay. Number 4, Fresnel integrals and oscillations. Number 5, Cornu spiral visualization. You will enjoy the 5th one. Number 5 will be a visual simulation. I'm going to show you a simulation of a Cornu spiral. Okay, it's a really cool spiral that I want you to see. You may have heard of spirals. Number 6, exponential integrals, and number 7, hopefully some research problems along the way. Okay. Hello, I remember you just letting it. Hello. Yes, it's good to see you again. I see you've been keeping track of my videos. Perfect. Thank you. Thanks for being a subscriber and for supporting the channel. Okay, today we're going to learn about an interesting type of family of integrals, okay, that you haven't seen before, but they're going to be very handy. All right. Okay, very handy for solving more complicated integrals. Okay, so that's what we're going to be doing today. All right, so let's get to it. Okay, if no one has any questions in the meantime. So why special functions exist? Okay, so we're going to talk about special functions. Unless anyone has any questions at the moment. If not, I'm going to get started. All right, so special functions, right? Special functions, they exist purely for what I have on the board. I've already written it because ordinary calculus, right? When I mean ordinary calculus, I mean, you know, like limits, derivatives, integrals, and stuff like that, cannot express solutions to many real physical problems. Okay, so what do I mean by that? Physical problems. Okay, anyone have any idea, like in terms of physical problems, physics, or anything like that, how integration is tied into that? Anyone at all? If not, I'll get back to it. Okay, if not, I'll get right into it. Okay, so what I mean is that quite often, because calculus and physics go hand in hand, actually, right? However, though, what happens in physics quite often, for those of you who know it, is that we don't look always at perfect, lots of times, we don't look at perfect situations, okay? Quite often, physics problems are only in abstract and theoretical cases, okay? They don't have, I'm not saying they don't have connection to reality. Most of the times they have a connection to reality, but sometimes we're looking at cases that don't mimic exactly what's happening in reality. Okay, so when that happens, ordinary calculus will not be able to help us solve many of these problems. Okay, so we have to use more advanced integral methods or any other mathematical methods to help us solve these physical or visual spatial problems in the real world, if that makes sense. Okay. All right. So let me get to it. All right. So most of these integrals that we're going to see have no closed form. That just means that there's no elementary functions. Okay. Right. So there's no elementary functions that can solve these problems, but they constantly keep coming up in a lot of different areas. Right. As I mentioned, physics, probability, engineering. They even happen in something called stochastics. Stochastics is a part of probability, but sometimes it's separate. It's more or less the same thing. Okay. All right. So quite often, experts in the field have to define a new function. Okay. So math experts usually have to define a new function when dealing with situations like this. Okay. Anyone have any questions, any conceptual things that they want to go through on this topic? Anyone at all? Anything at all? Just let me know. Okay, yes, I'll continue. All right, so continuing on, right? We're going to be looking at the special functions, right? The error function, right? As I mentioned, Fresnel and the exponential integral. Okay, these are all in my book, by the way. If you're ever interested in getting it, they're all there. Okay, so yes, we're going to look at each one of these special functions. Okay. Now we get into some interesting stuff today. Something called the error function. Okay. I don't know if any of you heard of the error function. Right. If you have heard of it, maybe put something, thumbs up in the chat. If not, yeah, I guess you have to say anything, but just want to see if anyone in the chat is. I don't think so. Oh, okay, yes, just another new guy. Yes, the error function, you will hear of it, but they don't go in detail quite often in college or university. It's some type of, it's a mixture of a Gaussian integral, as you can see below. Okay, right? So as you can see, what I've highlighted in green is my error function equation. Okay, and the error function, right, is a function defined, erf of x, right, is equal to the constant 2 over root pi times the integral from the lower bound of 0 to the upper bound of x of e to the negative t squared dt. Right? So you can see there is a relationship with the Gaussian integral of any type of Gaussian symmetries. Okay. All right. So I want to show you guys something interesting if possible. I'm going to see if it's going to work. All right, so let me just go back to the desktop. I want to show you a simulation, if possible, to make this stuff come alive, right? Not just me showing you me solving equations all the time. I want to get this more interactive. Okay, just give me a sec. Stop sharing. Let me see here. So I'll stop sharing for a second, and I'll go directly to screen. Let me see here. That's me. Okay, just give me a sec if it's going to let me do it or not. It's going to let me do it. Let me see here. Just give me a sec, guys. Okay, I might use this. Yeah. Okay. Yeah, just give me 1 sec. Right? Give me 1 sec. I'm just trying to pull up some interesting simulations, okay, of the error function, if possible. I use some coding and programming to make these simulations. Yeah. Okay, so we're going to go here, right? So let me just, if I can share a screen of the window. Okay, I'm going to share a screen right now. As you can see, right? Okay, so here is a numeric versus an integral approach to a Gaussian symmetry. Okay, so what we've got here is we have an integral, okay, of e to the negative t squared, regular Gaussian. Okay. However, though, you can see that the shape is slightly different than just a regular bell curve, as those of you who already know of, e to the negative x squared. Okay. This one is supposed to be giving us the error function. Remember what I said about the error function? Okay, it's always 2 over root pi integral of 0 to x of e to the negative t squared dt. Okay. All right. So what I'm showing you here is exactly that. Let me just go back again so you can see it. So this curve doesn't go all the way down. It's not it's not asymptotic like the regular bell curve when you take a Gaussian integral. Here you have a numeric versus a symbolic integration. Well, all I'm saying is that I'm showing it both by, either Simpson or trapezoidal rule for those of you who know integration by numerical methods, and also just a regular integral, okay, as you can see here. All right, so I'm going to run that again. Okay, all right, so as you can see, as I said, I plotted f of t in the t-axis, right, of e to the negative t squared. Okay, and we get a really interesting curve. And you can see here, it gives us some attributes. You can see that integral, right, our integral for this would be root pi over 2 times e, right, to so say negative t over something right there. That's what that integral of the error function should be. Okay, so let me just get out of this. Go back to stop share. Okay, and any questions on that? Any questions on the on exactly what we're talking about here, right? Any questions on the simulation? Possible. Hope you enjoy that. That's trying to make things interesting. Okay. All right. So, okay, perfect. Looks great. Yeah. So I just want to add more simulations to my teachings and lessons. I feel like when you're doing math, it's good to have a unique perspective that works. I feel like having drawings or simulations, graphs really helps bring it, like giving you a comprehensive look at things, not just algebraically solving problems, but also giving you a model as well. Okay, so that's when it comes to the error function. Okay, right, and I'm giving you not just that, I'm giving you an explanation of what the error function measures. Okay, just like the simulation I showed you. Okay, you're going to see that the error function, as you was shown there, measures the cumulative area, right, under a Gaussian, if that makes sense, right? That's what it measures. Okay, so here I'm just giving a regular Gaussian, a Gaussian bell curve, right? A regular Gaussian bell curve looks like that, right? All right, so the cumulative area under that Gaussian, all of this is what we're pretty much measuring for the error function. It's not exactly drawn accurately, but I try my best. My hand pen drawings aren't the greatest. That's why I'm leaving it up to simulations with programming. If that makes sense. Okay, so that's what we have. Right, now, another thing about the Gaussian is it's symmetric, right? It's symmetric, right? So obviously, in the middle. Speaking of the Gaussian, does anyone know if you have any statistics background, what quantities that it gives us? Oh, yes. Those are, I have my papers. If you can tell me how this gets regarding. Oh, yes, I'm getting to that. I didn't see you. I'm gonna get there right away. Live, gamer, visual. Yes. I'm gonna get to that right now. How to graph a quadratic, right? Okay, so let me just get to that. All right, so we're just going to divert for a second. Okay. Okay, so let's say you have a quadratic. Let me go to page 7. Just give me 1 second. How to graph, right? Just how to graph quadratics. So how to graph quadratics. Okay. When it comes to graphing quadratics, I'm going to put certain definitions that are important. Definition 1. Okay. For instance, let's say a quadratic is either in the form of y equals ax squared plus bx plus c, the standard form, or in factored form, y equals a parentheses x minus r1, where x minus r1 is a factor, x minus r2, and so forth, right? So let's say definition 1, I give you it in factored form, right? So in factored form, a quadratic is written like this, okay? Is written like this. Okay, so let's say, for instance, y is equal to, I'm going to highlight here, y is equal to a parentheses x minus r1, x minus r2, right? Highlight this formula. This is really important. This is the factored form of quadratic equation, okay, where a is a vertical stretch or compression, r1 is root, r2 is a root. So far, this good? Oh, yes. Good. I'm glad you're liking it, live gamer. I'm going to continue. Just another guy. Is it the same as a normal distribution? Yeah. Bell curves are the same as a normal distribution that I put up there. Yeah, of course. But my initial question was, it is a normal distribution, but since it's a normal distribution, what quantities are we measuring for that bell curve? Just another internet guy. What do you think? What do you think? Don't worry, live gamer. I'm going to get back to your question. I'm just going to continue. Okay, live gamer. Just an internet guy, think about that for a second. What quantities that you can measure on the bell curve? Live gamer, I'm going to get to your question right now. Yeah, probability density function. So think of hints, means, mean. Well, that's one of the quantities. Yeah, I'm coming live gamer. Just 1 second. All right, so live gamer, I'm going to get to you right now. So we've got in factored form, right? We have quadratic written like this. Okay, I'm pretty sure you've seen it. Okay. R1 and R2, I'm just highlighting R1. R1 equals root 1, R2 is equal to root 2. All right. Root 2. Okay. That's definition 1. Definition 2, now I'm going to mention was also to mention what A is. A is the vertical stretch of compression. Vertical stretch slash compression. Okay, that's what we got there. Now, how do we get these important quantities? Okay, how do we get R1 and R2? Let me explain. Okay, so if you have R1 and R2, right? Let's say this is R1, this is R2. I'm giving you a visual here. Let's say the vertex is located down here, right? So vertex V of H comma K, right, is something like this. This is your parabola, right? So here is a root, here's a root, here's your vertex. Okay, just giving you a theoretical thing right now. All right. Does that make sense? Okay. Yeah, exactly. Yes, exactly. Yeah, just an internet guy is answering your question too, right, live gamer? And the roots of the x-intercepts. Okay, so I'm just getting back to it. So R1 and R2 you can get from a graph. If they gave you a graph, right, and the graph has some roots, you know what your R1 and R2 is. Let me give you an example. Okay. Oh, before giving an example, there's one more thing I need to tell you about. Actually, No, I think we're fine. I think we're fine. We can do the example right now really quickly. Okay, so let's say you have an example like this, right? Let's say the graph is like this. Let's say you have an intercept over here at -1, -1, 0. This one over here is at, I don't know, let's say 2, 0. Okay, let's say down here, yeah, -3. Okay, -3, negative x is, oh yeah, sorry, x is, let's say 1 comma -3, for instance. Okay, something like this. And they say find the equation of graph, right? Equation EQN of the graph. Any ideas how you would get the equation of the graph using starting in factored form, right? You want to take this as your starting point. Yes, that's correct, just an internet guy. Yes, standard deviations from the mean to approximate. Well, we're not really looking for a specific value. I'll just give you a conceptual thing there. But yes, standard deviations is not the quantity, right? It's certain standard deviations away from the mean for the bell curve, right? Plus or minus sigma, right? Plus or minus the standard deviation away from the bell curve, right? That's what I was talking about. That's exactly what I was talking about. So certain standard deviations away from the mean, plus sigma for the right-hand side of the bell curve, negative sigma for the negative side of the bell curve. Okay, so plus or minus sigma, if that makes sense. Okay, so mean, standard deviation, those are the quantities that you mainly go with the bell curve. We can put roots, I think. Yes, that's correct, Live Gamer. Just 1 second. So Live Gamer says, yeah, we can look at the roots. Okay, so we have roots here, right? We have -1, 0. Okay, -1, 0. So what we would have, right, is that we would have y is equal to a bracket x minus -1, right? This is my x minus r. Okay, this is my x minus r1 for the first factor, if that makes sense. Okay, and then my second factor will be x minus r2, x minus 2. Okay, does that make sense? I already got a good part of the equation underway. Okay, so y equals a parentheses x plus 1, right? And then x minus 2. All right, good, yes, excellent. Okay, so now we have that. Now the thing is, we still need to figure out what a is. And how do we get that? We get that by just choosing a point on the graph. It has to be on the graph first off, okay? It needs to be on the graph. You should all know that. That's elementary. You have to have a point on the graph, okay? And such that it does not make the a value 0. Because if the a value is 0, the whole equation collapses. You don't have an equation, and that wouldn't make any sense, okay? So it needs to be a point on the graph such that a cannot be 0, okay? So let's choose 1. Let's use the vertex coordinate that we found. Doesn't matter which one we use, 1, -3. Okay, so I'm going to look at the location using these specific coordinates at 1, -3. Okay, y is -3. A we're looking for, right? So a parentheses x is 1, 1 plus 1, 1 minus 2 here, right? Solve for a. -3 is equal to a by 2 times -1. This gives you -2a, sorry. -2a is -3. Solve for a. A is equal to 3 over 2. Substitute into our original equation. So therefore you get y equals 3/2 of x plus 1 times, therefore the equation is y equals 3/2 times x plus 1 times x, what was it, x minus 2, I believe. X minus 2. That's the equation of the graph when you're given a graph, if that makes sense. Yes. Well, it could have been any value, any point on the graph, as long as it's a point on the graph. Does that make sense? That makes sense? Good, excellent. All right, so let's get back to it. One more thing I want to talk about that's very important, okay, is this. Okay, so that's when you have to deal with graphing, when you want to find the equation of a graph which has the roots, okay, when you have roots. like the x-intercepts. Now, what if the graph, let's say you have something like this. Okay, I'm going to give you one more thing, another definition here that's very important. Standard definition of a quadratic equation is y equals ax squared plus bx plus c. Okay, let's say you have something like this. All right, so that's the standard form. Standard form of a quadratic, where a, b, and c are constants. Okay, all right, and I have to make another page here. Okay, so I go to new page, page 8. Definition 2, which is very important. Definition 2 is this, axis of symmetry. So to calculate the axis of symmetry, 1 second here, axis of symmetry is to use this equation. X axis of symmetry is equal to x1. x1 is root 1 plus x2 divided by 2. And why would we need this? Because quite often when we're dealing with quadratics, they ask us for the vertex. And the vertex has the x-coordinate, which is the axis of symmetry, and the y-coordinate being, it's brain fart today, the k value, right? Vertical translation up or down. Axis of symmetry has to do with the x-coordinate of the vertex. The x-coordinate, okay? Quite often we need that. Okay, I'm going to explain why. Okay, so for instance, let's say you have a question like this. Here's a question. Okay, so let's say you have y equals, let me think. Let's say you have y equals 2x squared equals 3x plus 5. I'm thinking of the question here. Just give me a sec. Y equals, sometimes coming up with questions is tricky. Y equals 2x squared plus 3x plus 5. Get the reach, you need to make sure that you're, I can't think of the question. 2x squared plus 5x plus 1. Okay, let's say you had y is equal to 2x squared plus 5x plus 1, right? Like this, something like that. And it goes at, and this equation is going through the point 1, 0. Okay, and you wanted to determine, find, let's say the question said find the vertex coordinates. Coordinates. Okay. So say you want to do that. Okay, so we're going to figure out what the vertex coordinates are. Yeah, you can do minus b over 2a. Yes. Yes, exactly. Minus b over 2a is correct for the vertex. You could also have done, as I said, x-axis of symmetry, x1 plus x2 divided by 2, for to get the roots of it, and then after average it, get the axis of symmetry. Okay, so you could have done it that way. Yes, but we're going to look at, just 1 second. I'm trying to make a, oh yeah, sorry. I should have made it in vertex form. Not vertex form, in factored form. Y equals 2 by x plus 1 times x minus 3. And let's say I said find the vertex. Yeah, find vertex coordinates. What you would do, right, if you want to do it, is b over 2a, as you mentioned, or the x-axis of symmetry equation. So I'm going to do that. So x1 plus x2 divided by 2 is equal to x AOS. And then this is going to be equal to x1, right? X1 would be -1. This would be positive 3, right? Because we solve for the roots, okay? Divided by 2. 3 minus 1 is 2. 2 over 2 is 1. You have your x-axis of symmetry. So x AOS is going to be equal to positive 1, sorry. Okay. And then to get the y-coordinate of the vertex, substitute the x-axis of symmetry back into the equation. So y is equal to 2 by x plus 1. Okay, 2 by x plus 1 times x minus 3. Substituting what the x-axis of symmetry is to get the y-coordinate. 2 by 1 plus 1 by 1 minus 3, right? Very easy. So y equals 2 by 2 by -2. 2 and 2 is 4. 4 and -2 is -8. I get the y coordinate as well. Okay, and that means my vertex coordinates v is equal to 1 and I think it was 8. Yeah, because the y coordinate changes. 1, 8. And those are the vertex coordinates. Okay. 1, 8. Any questions? Minus b over 2a. Yes. Yes, that's right. A live gamer. I hope that helped a lot. I'm glad you're enjoying the live show. Yeah, I hope that helped. That's my job, anyways. But I have to get back to the overall. Oh, perfect. Perfect. Well, I hope you become a subscriber. Oh, perfect. Thank you. It means a lot. I hope it goes well, and stay tuned for more live shows. I'm going to get back to the original stuff that I'm doing on the live show. Oh, perfect. Great. Excellent. Stay tuned for more live shows. It'll be very handy. But I'm going to get back to this live. This live show might be a little bit crazy what I'm doing because it's not about quadratics. It's more about integral calculus. But yes, I'm going to get back to that. But stay tuned for more live shows. I appreciate it. Okay. Yes. Yes, they get pretty it's pretty crazy there for my book. All right. Thanks, live gamers. See you next time. Okay, so we're going to get back to it. Just there, guy, just hang in there. We're going to get back to bell curve stuff that I was talking about. Okay. All right, so let me just go back to it. I want to share my screen. Okay, so we were looking at the bell curve. I was talking about that. Yeah, okay. Yeah, we're talking about the bell curve. So as I mentioned, right, plus or minus sigma everywhere. Okay, plus or minus sigma. So this is positive, yeah, positive sigma here. Okay, so this is going to be positive sigma. So that means certain standard deviations away from the mean. Okay, I'm highlighting that one with little sigma. Sigma means mean. I mean standard deviation. You should know that. Mu is located right here. This is the mean on this axis of symmetry of the bell curve. If that makes sense, right? And then over here, this would be like a negative sigma away from the mean. If that makes sense visually. Okay. All right. So as I mentioned, right, the Gaussian is a symmetric function, is a symmetric error function, actually. Right? As I mentioned in the simulation, you can see that there's a relationship between the Gaussian and the error function. Okay. And the applications for this, it usually has to do, it's really interesting, probability, right? A lot in probability. Right? Gaussians are very important in probability. Okay. We're not going to be looking at probability in this live show, just the applications of integrals in probability diffusion, and heat flow. I'm going to talk about that stuff, right? And this pretty much is the bridge between calculus and statistics. Any questions on that? All right, so nothing yet. Okay. All right, so we're continuing again here, right? All right, so we're going to look at another type of integral that we're going to be looking at, right? And this is applied to probability and the heat equation, okay? Right, so the heat equation is just is something called, it's has to do in math and science, but the heat equation is a PDE, okay? And the PDE, we're not going to talk about PDEs here like in depth, no way. Okay, but we're just going to say here that a PDE is a partial differential equation. Okay, so there's a numerical way to solving PDEs, which is easy, and then there's a hard way. We're not going near that either one, but I'm just going to give you the general lowdown here. It's defined below with the following equation, and the heat equation PDE is defined as U sub t equals K times U double X. In other words, this can be written as the following. Just if you want to see the notation here, K times di squared u di x squared, where di u di x is a partial derivative with respect to x. Okay, any questions on that? Oh, I'm really enjoying that you're loving it, just didn't guy. Oh, what is it? Do you have a question? Sorry, I got confused. Oh, okay, there's no question. Okay, there we go. I think I understood. Yeah, let's get back to it. Okay, perfect. All right, so heat equation, right? So you have a PDE defined below the following. Okay, right. So this is what we're not going to get into that really, right? Because you don't. I mean, there are some PDEs in my book, but the PDE is. Do I go through PDEs? No, I go through regular differential equations. Yeah, it's good if you have well, if you understand calculus, you have background in integral calculus, differential equations is easy. But we don't talk about PDEs, but the application of PDEs and this type of integrals that we're going to be looking at go hand in hand. That's why I just pulled it up. Okay. So the heat equation, right, just to give you an application of what it does, is a solution to a Gaussian, okay? Solution to Gaussian integral, right? Right? Well, sorry, heat equation solution is a Gaussian integral. Yes, I have written down. Okay, so all that means is that if you were to take this, okay, if you take this equation, right, and quite often for PDEs numerically, when you solve them, you use something called separation of variables. Anyone know what that is? Anyone know how separation of variables works if you've taken elementary calculus or first year differential equations class? Separation of variables. Yeah, exactly. Yeah. Just another guy who is just nailed it. He's right on the money. That's exactly how we do separation of variables. Okay, so we take certain variables, one isolate one, the other one isolate on the other side, integrate, and put that arbitrary constant because it's an indefinite integral. Yes, that's right. And practically almost the same thing is happening here. But yeah, that's exactly it. Okay, so we're using the error function, right? So this is uses the error function, right? And obviously, when you do these, for those of you who know differential equations and stuff like that, boundary conditions are usually involved, right? Same thing for differential equations, partial differential equations use them as well. Boundary and initial value conditions as well, and other things as well. Okay, so in probability, right? If you have an error function, right, the error function determines the distribution of noise quite often, noise, measurements, fluctuations, signals, and stuff like that. Okay. All right. So those are the mathematical applications. Okay. Now I'm going to show you. I might be able to bring up another simulation from back in my coding days. I love doing simulations, so I'm going to incorporate that with my lectures sometimes, or quite often actually. So let me get back to the desktop. I'm just going to stop screen and let me just do it again. So let me stop screen temporarily, stop sharing. Okay, then I'm going to go to, just give me one moment. Get out of that. Just give me 1 second here, guys. 1 moment. Okay, so let's see if I can pull this up. Okay, yeah, so the heat diffusion I want to talk about here. Okay, so just give me a moment. Okay, I'm going to start sharing my screen again. Share screen. And we're going to look at this guy right here. Okay, so if you can see here what I have, okay, this is the media player. And we're going to look at the heat diffusion, okay? So you have a spike when you have to deal with, an error function. Like the solution to the heat equation is a Gaussian, symmetric Gaussian, which is an error function. Okay, so let me just go again and explain what's happening here. So you can see that we have a spike in our, our bell curve, right? And you can see what's happening, right? So as the bell curve stretches more and more, right, the time parameter is increasing. Okay, so let's look at that again. All right, so you can see here that as time increases, right, it goes from narrow to more stretched for the bell curve. And at the same time, we can measure the diffusion length as well, which is the square root of 4 kappa t, right? So let me just show you one more thing here. So we have the square root of 4 kappa t, all right, is the diffusion length. That's a formula. It's an interesting formula. You can calculate interesting things about the heat diffusion from the heat equation. Okay, so let me just show you again, because there may be some other things. Another thing too, the temperature is on the y-axis and capital X is on the x-axis. Okay, so it's a Gaussian. The blue represents the Gaussian heat kernel, the orange error diffusion wavefront. Okay, all right, so that's what's happening here. Okay, it's a pretty interesting concept visually. You see what happens. So as t increases, my diffusion length increases, right? So it's that's how it works. Okay, let's get back. Let me get back to it here. All right, so let me just get back. Stop sharing. Yep, stop sharing. Just 1 second. Yeah, just 1 second. I'm going to get back right into looking at. So let me share my screen again. Okay, there's your screen. I'm going to share. Okay, so let's get back right into it. Okay, so we're going back to the whiteboard here. Okay, so we're moving away from probability and the heat equation. Okay. Now, another type of integral that is very important, okay, is going to be something called Fresnel, okay? Fresnel integrals. Just 1 second. Someone's giving me a problem here. Okay, Fresnel integrals, okay? And they're applied to something called wave diffraction. I'm going to talk about that in a moment, okay? So it's always good to have water when you're talking a lot. Okay, so a Fresnel integral, right? So Fresnel integrals are a very interesting type of integrals. And you can see based on both of these integrals, a lot of you will notice that they don't have necessarily elementary forms, elementary solutions to their integrals. I will show you actually there are ways to integrate these functions. Okay, there are ways to integrate these functions. I'm going to go through it, but I'm not going to complete the problems that I'm going to post on the cosine and sine Fresnel integrals. Okay, and the reason why is because I feel like you guys have the background of integral calculus, so you should be able to do it. But once you see me start the process, I think you'll be able to take it from there, so you can try them for homework. Okay, but let me explain more about Fresnel integrals before we get on, unless there's any questions. Yes. Yes. Okay, so just an internet guy is really on board here. Yes. I'm assuming you must have taken physics in university or something. Yeah. Yeah, they talk about Fresnel a lot in optics and waves in physics. Yeah. Yeah. So it's going to be very handy in that sense. Now they haven't gone into it deeply. And if they've done anything with the integral, they probably just talked about application. But I'm going to talk more mathematically how you can deal with these things in a moment soon or later on. Okay. So Fresnel integrals runs a capital C of x. Okay, that's the cosine Fresnel. Okay, so cos of pi t squared over 2 with respect to t. Okay, and then the other one is the sine Fresnel, capital S of x, integral from 0 to x sine pi t squared divided by 2 dt. That makes sense. Okay. All right. So we're looking at that guy right there. So we look at the Fresnel integral. Sorry about that. Fresnel integrals. Okay. So let's go to the next page. Sorry about that one. So Fresnel integrals. All right. They describe how waves bend around edges. Okay. And the phase of a wave, right? Phases of waves and stuff like that, right? So as just a guy pointed out, that's exactly what they're for, right? Telling us how, describing how waves can bend around edges, and other things too, right? Wave and how the wave increases, but actually increases in a quadratic way, actually, okay, which is pretty interesting. So I know I'm getting a little bit off topic. We're going into more into physics right now, but I'll get back to math. So if you have like a diffraction wave or whatever, right, or optics, the integral stops behaving like a sine wave, okay, and it starts behaving something called a Cornu spiral. Yes, I'm sure none of you have heard of what a Cornu spiral is before, right? But that's what happens with Fresnel integrals and Fresnel-type functions anyways. They start behaving like Cornu spirals when we have to deal with diffraction or optics. Okay? Anyone know what a Cornu spiral is? Cornu spiral. Cornu spirals. Anyone know about Cornu spirals? Okay, I'm going to show you something interesting here. Well, we're looking at another simulation. Okay. Okay, so just give me a moment here to get organized. Rid of you. Okay, so where's my Cornu spiral? Just 1 second. Okay, so let me share screen. Share screen. Share the screen. Where are we? Okay, so let's get to share screen. Now, I want you guys to pay attention. Okay, so this is a Fresnel type of spiral. Okay, so this is a Fresnel integral. Okay, and you can see it looks pretty cool, doesn't it? Okay, so a Fresnel integral has the Cornu spirals. Okay, creates Cornu spirals. This is how they behave. Okay, on the x-axis, we have something called capital C of x. That's the cosine Fresnel integral. Okay, if you're paying attention on the shared screen. So in the simulation that you can see that I've modeled here, C of x is the cosine axis, capital S of x, and the y-axis is the sine axis. And what ends up happening with Fresnel integrals is that they form these double spirals, okay? The lower spiral is located in the bottom left corner, right? And the top upper right corner is the upper spiral. Okay, so you can see that there's something interesting happening with the behavior of these spirals. Okay, let's play this one another time, another go at it. Okay, so you can see here. So following this trajectory, they make the spiral, right? And they go up like that. Okay, so it's a pretty interesting curve. There's a lot of different types of spirals. Okay. In a second, I'm going to ask you if you guys know any other spirals. Have you seen any other spirals before? Okay, so you can see here that we have really interesting stuff. Obviously, if you're to look at some properties of these spirals, let's say the domain, range, stuff like that, right? So let me just show you again, right? For those of you who remember your grade 9, 10, 11 math, the domain is, what would the domain be? It will be all real numbers for those of you who are looking at this, right? Because it's spreading throughout the x-axis infinitely, right? So yeah, x belongs to R. In this case, we would say capital C of x belongs to R because that's our independent variable on the x-axis. Capital C of x belongs to R, and the y-axis being S of x, it's just going to be S as a function of x belongs to R, right? Okay, because there shouldn't be any restriction or bounds on that. All right, so that's the model of a Fresnel integral known as a Cornu spiral. Okay, I hope you enjoyed that. Okay, so let's get back to the live screen. Okay, so I hope you were enjoying that simulation. Okay, so let's get back to the share screen. Okay, just 1 second. Just 1 second. Why does you not a fan? Yes. Shudo is is funny. When his God hates trigonometry, he's not a fan of sin. Ah, that's brilliant. That's very funny. That is funny. That's good. Yes. Shudo, are you you're new to the channel? I've seen you before. How's it going? What are your interests? Are you a math high school student, university student? Just let me know. Oh, okay, perfect. Well, I hope you'll like and subscribe, and that you will enjoy the entire live show. Plenty of jokes, plenty of math jokes coming, plenty of math, interesting math concepts uh, coming up. So stay tuned. Okay. Are you in high school or university? I'm just curious. Shudo. Just let me know. It's just want to connect with the audience, know a bit more about you guys, if it's so I can help you guys. Oh, comp sci. Nice, nice, nice. I'm taking Calc 2 and currently on Calc 3, so pretty basic stuff still, but trying to practice and learn more. Okay, all right, perfect. Well, you hit the right place. As I said, I'm a bit about me. I'm an author and a tutor when it comes to advanced math. So you're in the right place. We specialize in advanced math. Okay. So especially when it comes to calculus and linear algebra and stuff like that. Okay. Trying to show you some really interesting toolkits that you can add to your mathematical toolkit to solve university and undergraduate related problems. Okay, so that's what we're going to be doing right out of my book too. Okay. Glad to hear it, you though. We're getting right back to it. Okay, so let's get to it. All right, so we're going to be looking at this interesting concept. I'm going to get right to it right now. So let me share screen. Where was I again? Let me do the entire screen. The time we're going to go to the whiteboard. Okay, back to the whiteboard. All right, so before looking at a problem, okay, we're going to be looking at something called the exponential integral. Okay, this is the last type of integral definition I'm going to go through. Okay, I have to go through definitions, whether you like it or not, because otherwise, a lot of you won't understand what I'm doing. If you haven't seen it for the first time, I have to give some sort of mathematical theory behind what we're doing before we look at a problem. Okay, so we're going to be looking at the exponential integral. So an exponential integral is defined by this symbol right here. Just 1 second, guys. EI of x, okay? That's what an exponential integral is. Okay, so that's the symbol, capital EI of x, EI of x function, okay? And formally it is written below as EI as a function of x, okay, is the integral from minus x to infinity of e to the negative t dt all over t, all right? So I want you guys to integrate that into your minds. Pun intended. Integrate it into your minds. I couldn't help it. All right, so this exponential integral, yeah, is really handy. Don't know if you've come across this or if you come across integrals like that, but it will be really handy for your mathematical toolkit. Even if you haven't used it per se yet in your studies, it's always good to know things that can help you down the road. These things pop up regardless. Okay. All right, so it's the integral from minus x to infinity of e to the negative t dt all over t. Any questions? So far, no questions. All right. Good, 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 good. So let me continue. All right, so we're ready now to be looking at So all, as I mentioned, before we get to it, right, looking at the problems, all this stuff, all these concepts are related, once again, to my book right here. For those of you just coming in, Advanced Integration Techniques, okay, where we master advanced integrals and applications. Okay, so if you're a undergraduate student who has background in integral calculus and linear algebra, then this may be the book for you as a supplement for your courses. Okay, again, as if you have a background in integral calculus and linear algebra, this is the book. This is the book to get. It's talks about mastering all advanced integrals, right? So building up from your background in integrals, from elementary to medium to hard to harder. Okay, and it helps for calculus 1, calculus 2, calculus 3, complex analysis, numerical analysis, and also in applied areas like stochastics, probability, and even quantum physics. So for those of you who are interested in learning more on this to advance your mathematical toolkit, you can get my book, and it will be in the description after this live show. Okay, so just keeping it real there. All right, so let's get back to it. Okay, unless there's any questions. I want to make sure there's any questions. Okay, so far everything's good. Okay, so let's get to the research problem number 1. Okay. Okay, so what I mean by that is, because another thing about my book too, it's almost at the level of a research level book. It's an academic book. Okay, that doesn't mean that it's not for people who are in high school. If you're a gift, as I mentioned, if you're a gifted high school student or undergraduate student who understands calculus and linear algebra, you can do these problems. It's just building up on your problem solving skills. Okay. All right. So that's all. That's all is needed: linear algebra and integral calculus. All right. So we're going to be looking at a non-trivial erf-based integral. Okay. For those of you, as I mentioned before, that's why I mentioned what an erf-based integral is, the error function. Look right here. The error function is defined as this. Okay, 2 over root pi, integral from 0 to x, e to the negative t squared dt. I mentioned that earlier for those of you who are just coming in. Okay. All right. So let's discuss how we can use that. Sorry about that. That's research problem number 2. I lost track. I'm getting back right to it. Sorry, guys. Yeah, so we want to integrate this problem here. Okay, I as a function of a is equal to the integral from 0 to infinity of e to the negative x squared cosine of ax dx. Now, the whole point of a live show is not for me to keep blabbering. It's for you guys to communicate back and forth with me. Okay, so does anyone have any idea how, based on your knowledge of integration, when you can connect to solve this problem? Anybody? Let's see if anyone has ideas. Oh, perfect. Perfect. Yes, Shudo, just to let you know, yes, the book will be in the description of the live live show after the live show, or I can always post it here, www.stem1online.com. All right. That's where you can get, you can purchase my book. Okay, there's a digital copy, sorry, and or a paperback. Right, so that's for Shido if you're interested. Okay. Let's see, and it'll be really handy for your courses. Just another internet guy. Wait. Is this Feynman trickable? Yes, you're right. Just another internet guy. Yes, you're getting right into it. That's right. You're right on the money. Just another internet guy. Feynman trick. Let's get right to it. Okay, so Feynman trick. Now, as you can see here, okay, this integral, okay, is yeah, you can integrate with Feynman trick. All right. Now, for those of you coming in, I'm going to do this really fast on the side. Okay. Oh, do any of you other guys know what Feynman trick is? I just want to make sure. I want to make sure you guys, anyone else understands what Feynman trick is. Anyone? Okay, so I'm assuming not. Okay, what I'm going to do is, just another guy knows what this is. As I do the problem, I'm going to give a slight definition of what we do with this. Okay, so, but I'm going to go right into the problem. Okay, so what we have to do is we have to, when we do Feynman trick, it's an approach used to calculate advanced integrals that cannot be calculated using elementary methods like U substitution, integration by parts, tables, power or rule for integrals, and stuff like that. Okay. And what we do is we put a parameter a here. Now, this integral already has a parameter a, right? Quite often, you're going to have to choose where your parameter goes in the right position of your integrand, that means the function, such that once you've positioned your a in the right place, you're going to differentiate both sides of the equation with respect to the parameter a, but you want to differentiate both sides with parameter a, such that once you've differentiated both sides, you can finally integrate the function. Okay, so let's do that right now. So I of a has already been taken care of. Now, what I'm going to do is I'm going to differentiate both sides. That means I have to do the following. Okay, I'm going to do this. It's going to be di, right? So di with respect to dA. I'm just differentiating both sides is d by dA, and I integrate from 0 to, trying to make my integrals better, integrate from 0 to infinity's improper integral of e to the negative x squared cosine ax dx. So once you have your parameter a there, you just differentiate with respect to the parameter on both sides. Okay? Right, hope that makes sense. Right, so now we have that. Now, from this point on, okay, once we differentiate with respect to both sides, I can move my differential operator inside the integral. You should all know that, right? I'm going to use white now. So dA is equal to the integral from 0 to infinity of d by dA, parentheses, e to the negative x squared times cosine of ax, parentheses with respect to x, if that makes sense. Okay. So again, as I mentioned, for those of you who don't understand what Feynman trick is, it's only used when you have a very advanced integral that cannot be integrated due to elementary methods. And what you do is you create a parameter, doesn't matter what you call A, B, C, whatever, I called it A, okay? You put your A inside your function here, okay? But it has to be positioned in the correct place, such that afterwards you're hopefully able to integrate the function elementary, like by elementary methods, or by some other method that is already known, okay? Right, and that's step 2, you want to do that. And then step 3 is, once you've done that, once you differentiate both sides, you integrate the original function, and you'll get a solution for I prime of a, the derivative. Okay, derivative of with respect to a. But then you would have to integrate again, because you have to get rid of the I prime. You want to find the original function I of a, because that's what we're calculating here, what this I of a is. And it will be I of a equals something with some boundary conditions. And then you solve for your boundary conditions, and then you should get I of a, which is the original integral. Okay? Right, I hope you guys are enjoying it, enjoying what's going on. All right. So let's continue here. Does anyone know how to do this? So remember, I'm differentiating with respect to a. differentiating with respect to A. What happens? Right, I'm differentiating with respect to A. Okay, anyone tell me what I do here if I'm differentiating? Just chain rule the cosine. Yeah, you're right. Yeah, just an internet guy is right on the money once again. Yes, that is correct. Yep, very clever idea. Yep. Okay, so dA, right? So dA equals integral from 0 to infinity. D by dA of this, that means that everything else is a constant, right? So if I'm differentiating with respect to A, right, all the x's are constant. So this now becomes x times e to the negative x squared. Derivative of cosine is sine, so it's negative x e to the negative x squared sine of ax dx. Okay, and the negatives go in front, right? It's just good to write it like this: minus integral 0 to infinity of x e to the negative x squared sine of ax dx. Okay, and this is my di. This is my dA. So do all you guys agree, in a sense, right? That would be my dA. Okay, because I'm differentiating with respect to A, so everything else remains constant from the chain rule. Okay, right, so I'm pulling everything out. Right? That is dA. Okay, so minus the integral from 0 to infinity x e to negative x squared sine of ax dx. Okay, so we've got that. Right, because the x came out. All right, now we've got this. I might as well just write it like this. Doesn't matter. I can say I prime. I'm just going to say I prime of A. I prime of A is equal to minus the integral from 0 to infinity of x e to the negative x squared sine of ax dx. Is more compact this way. Okay. Probably following along on paper, but I'll definitely have to watch your video on the Feynman trick. I haven't seen that before. Okay, so yes, as I mentioned, it may be handy to get my book because it talks about the theory on the Feynman trick. Okay, actually, it talks about a lot of things. Okay, so that can be really handy for you, pseudo. You should check it out. It'll be and also be handy for your classes as well. Another thing too, because it breaks down a lot of concepts and gradually progresses from there. When it comes to Feynman trick, I do have another video. One of my other videos or live shows talks about Feynman trick. It should be labeled Feynman something. Look into the other, because I talked about that in my other videos. I do a lot of videos, so you have to keep up to date to it. But yeah, check that video as well. Okay. But just another internet guy. He's watched all my videos, so he knows about the Feynman trick. So we're going through that right now. Okay. All right. Now, does anyone know what we should do with this integral? Capital I prime of A is minus this improper integral of x e to the negative x squared sine of ax dx. That can be pretty annoying. Now, capital I prime of A is this. Okay. Now we have a problem. One of the problems is that we have a product of x e to the negative x squared times sine ax dx. So we have a mess. Okay, after doing all of this with the Feynman trick and then using Leibniz, the Leibniz technique is the same as the Feynman trick. Differentiate both sides with respect to the parameter a, and then after finding a way to integrate what's in our integrand here, which is this is our integrand, by the way, right? Our original function. Function of x and a, right? That's what it initially was. Anyone have ideas how to integrate the function? Yeah. Yeah. Okay. So I want you guys to think about this hard. Okay. So it looks like, mm, okay. U x e and negative x squared, sure. Oh, now careful with one thing. Careful with that. Yeah. So here, yeah, I know what you mean. Like u would be xe to the negative x squared. That's what just another guy has written in the chat. What you have your u and you have your dv, right? So you chose your u. You mean dv, like your dv would be the sine ax dx. I'm assuming, right? Because that's not v. Because integration by parts is integral of u dv equals uv minus integral of v du. If you remember it, right? Right. I mean, you can try that, right? Okay. So let's try doing something here. So let u, right, let u equal to x e to the negative x squared. Dv has to be sine ax dx. Okay, so we've got this. All right. Now I also have to find my du, my differential of u. So taking the derivative of this, okay, this is product rule, first function x, derivative of the second function would have to be minus 2x, yeah, minus 2x e to the negative x squared, right? Plus the second function e to the negative x squared times the derivative of x is 1, then differentiate with respect to x. This is a derivative, okay? Now, as you can see here, this will not work. How do I know that this way of doing integration by parts will not work? Well, what's telling me right away that it's a problem? I bet a lot of you who thought you knew integration really well until you came across this, then said, it's actually harder than you think it is. Any ideas on how to integrate this monster? Guess what? This, okay, if anyone can tell me right now how we integrate this. It may be better to do it like this, right? Let u equal sine as a function of ax, okay? Let dv equal, quite often you have to change around your u and your dv, because as you can see, when I chose my u to be x e to the negative x squared, my du came out with a huge differential. More likely, that's not what it's going to be, because when you have to integrate again, right, when you do integral of u dv is equal to u times v minus the integral of v du, okay? When you remember, you're going to integrate with respect to u. If my differential was that big, more likely it's wrong, right? Right. There's no way I'd be able to integrate x times negative 2x e to the negative x squared plus x, and then multiply by v, my antiderivative v, right? It would be like a catastrophe, a monster practically, right? So quite often with integration by parts, your integrals to become more clean and simple. If it's not, more likely it's incorrect, right? You're choosing the wrong u and your dv. Okay, so I'm choosing u to be sine ax. I'm choosing my dv to be x e to the negative x squared dx, if that makes sense. Okay. Now my du, if I take the derivative of cosine of as a function of ax, the derivative of sine of ax, sorry, that would have been a times cosine of ax. Okay, with respect to x. All right. And if I take my dv and I find v, well, to find v, that means I have to take the antiderivative, and I do that by integrating x e to the negative x squared dx. Okay, so any questions on that? Okay, so it looks like there's no questions yet. Okay, so we have these guys here. Okay, so if that is the case, okay, let's go to the next page. So we have our u, our dv, our du, and our v. Okay, so as I mentioned, my u equals sine of ax. My du equals a cosine as a function of ax dx, x dx. Trying to make my writing better. Sorry about that, guys. A cosine of ax and then dx. My dv now would have to be, let me see here. What did we say my dv was? dv was x e to the negative x squared. Yeah, x e to the negative x squared. Negative x squared. Negative x squared dx. My v means that I have to integrate this. Right, so integrate x e to the negative x squared dx. You guys should know how to do this. How do we integrate x e to the negative x squared? Anybody know? Integral of x e to the negative x squared dx. We have to do some type of integral technique to get the antiderivative of dv to get v. Because remember, we need to use integral of u dv equals uv minus integral v du. That is the definition or formula of integration by parts, right? So we need to figure out what v is, and we only do that by integrating, getting the antiderivative of dv. Anybody know? Anybody know how to do that? Yeah, just use substitution. That's right, just another internet guy. Just an internet guy is right again. That is right. Very good. Yeah, that's very good. Okay, so yeah, we really use substitution. Okay, so obviously you would just let me just make some room here. I have to make some room. Yeah, so we're just gonna do another substitution here. Let u equal to well, my u would have to be negative x squared. So negative x squared. And the reason why I did that is because to use u substitution correctly, I need to get a correct u in order to have my differential, to get a correct differential du such that I can integrate as a function of u, right? So if u is negative x squared, therefore my du has to be minus 2x dx, okay? See, this x dx is important here, right? Because I have the factor of x, and dx can be replaced with the du as long as I divide by negative 1/2. So negative 1/2 du is equal to x dx. Okay, and I'll substitute that in. So I can replace all my x's with u's and my du's with dx's. Okay, so that means that my v now, okay, so that means my v here is now just all of this, right? This integral of xe, let me see, x dx was the 1/2, negative 1/2 du, negative 1/2, negative 1/2, okay, e to the u, du, integral of e to the u is e to the u, so this becomes negative 1/2 e to the u, okay, negative 1/2 e to the u. Okay, so that's what we've got there. So we now know what our v is. Okay, well, let me put what u is. I forgot what u is. We have to put that in because we were initially integrating with respect to x. So u now, right? We said u was a negative x squared, so this is negative 1/2 e to the negative x squared, and that is v. Okay, so we have our u, our du, our dv, and our v. And now we can just plug everything in. Okay, for our integration by parts formula. Again, just to remind you, integral of u dv equals u times v minus integral of v du. Okay, so now we just, the initial integral that we were looking to calculate was, yeah, this guy here. Yeah, so I'm just going to put that in just to remind ourselves. So this is minus the integral, okay, minus the integral of x e to the negative x squared of sine of ax dx. Bounds were from 0 to infinity, I believe they were. Yeah, limits were going from 0 to infinity. Okay, is everyone following so far? Okay, I'm assuming you guys are following. Please let me know if everything's okay. Okay, so just an internet guy says everything's okay. I hope for the rest of you, everything is okay. All right. Okay, so let me just make sure. All right, so if you know integration by parts, you'll be able to follow what I'm doing here, right? So this is going to be, so we have that integral of u dv, and this is going to be u times v. Now look at u and v. U was this guy here, v negative 1/2 u x squared, so we can plug that in. So this becomes positive 1/2, let's see here, x squared, e to the negative x squared. Okay, so we got that part. So u times v minus integral of v, right? So v, this is my v here, okay? V du again, right? So this is going to be minus 1/2 e to the negative x squared. V, and then du is the minus 2x dx. Oh, no, that's not what it is. V was that negative 1/2 e to the x squared. My original du. Oh, good grief. I'm using the wrong ones. That was for my u substitution that I was using. Sorry about that, guys. All right, where were we again? Let's keep track. U times v. My original u, sine ax, right? We're going to use the u and v's and du's and dv's for the integration by parts, sine ax. So this is going to be sine as a function of ax. V, where's my v? V is negative 1/2 e to the negative x squared. So negative over 2 e to the negative x squared. I should put e negative x squared in front of the sign. Okay, I'm going to do that. I'm going to put it right. E negative x squared, sine as a function of ax, so all divided by 2. Limits of integration, we're going from 0 to infinity. Okay, minus the integral from 0 to infinity of v du. V was what was the v? Yeah, there it is. V negative 1/2 e to the x squared, and then du. So negative 1/2 e to the negative x squared. Okay, e negative x squared v, and then du was the a cosine of ax dx. It would be a cosine of ax dx. Okay, so this is what we've got right now. Okay, pretty cool stuff. And then this is just going to be equal to this, right? Negative, we can clean this up, negative x squared, sine as a function of ax. Okay, sine as a function of ax, all divided by 2, limits of integration going from 0 to infinity, positive 1 over 2a. So this is positive a over 2, integral from 0 to infinity of e to the negative x squared, and then times cosine as a function of ax dx. Okay. Questions? Any questions? So far, that should be okay for you guys. All right. Now, so far, this is what we've got. Okay. That's so far what we have here. Now, I'm not going to finish this. I've given you guys a strong base on how to do this. Okay. So I want you guys for homework to clean up the problem, right? Because this is a live show. So the point of the live show is to build a rapport and see from the theory that I've taught you, right? Based off of page 1, 2, right? All this stuff here and what you already know in your elementary calculus classes, right? What you can deduce by yourself, right? Okay. So based off all of this and what you know in your past calculus classes, how you can solve a problem like this. Okay. So I want you for homework to see if you can finish the problem. Okay. And there's multiple ways of doing this. It's not just integration by parts you could have done. I'm going to give you another hint. Yes, integration by parts is needed, but I'm going to have to give you guys a hint for this. Okay. That makes sense. Right. So I want to give you a hint here. So the hint is hint. You will need to use, I'm going to highlight this. You will need will need to use the error function as well at some point here. Okay, so the error function, as I mentioned, is error function is function of x equals 2 over root pi, okay, integral 0 to x e to the negative t squared dt. Okay. All right. So that will be part of the solution for this. Okay. So please do that for homework. Just an internet guy, I know you're interested in this stuff. I hope to hear if you've solved it in our next live show. Okay. By the way, the reason why I'm doing that, another reason why I'm doing that too, there's two other problems I want to give you, start off, give you hints, and see if you guys, perfect. Okay, glad to hear that. All right, so, because there's two other problems too, and there's only so much time I have, right? Okay, so let's get to the next one. I think there was a, did I have it here? Ah, boy. I can't find you. That was research problem number 3. That was the error function. Just 1 second, guys. Oh, I'm in a black in the universe, in a dark abyss. I can't find. Oh, there. Wait. Yeah, there it is. Research problem number 2. Okay, I have to also change something about this. So this is the sine Fresnel integral. Okay. Now the sine Fresnel integral, right? I want you to analyze the behavior. I shouldn't really say asymptotic behavior. I should be saying mainly see how you can solve this integral, like just evaluate it as opposed to asymptotic behavior. I have a lesson on asymptotic behavior. So if you also want to analyze its asymptotic behavior, look at another lesson that I talked about. It's a regular stream. I think it was a live show. I can't remember. I was teaching people about that. But if you haven't seen it, look at that if you want to analyze asymptotic behavior. But for now, in this live show, the problem is just going to be evaluate this interval. And the way you can do that, let me show you how you're going to do this. So here's the solution, at least part of the solution. Okay, you should know that sine x can be written as a complex exponential. Okay, and that complex exponential is e to the ix power minus e to the negative ix power divided by 2. Have you seen this expression before? Anyone see the expression? Please let me know. Anyone see this expression, sine in terms of complex exponentials? Anybody? Oh, never. Okay. Well, you guys are going to learn a lot of stuff. All right. So this is going to be really informative. Yeah, so the complex exponentials, sine can be written in terms of this. This is a formula, actually. It's a formula and definition. Okay, so this is 1. And there's 1 for cosine as well. But here we only need to use sine if we're solving this, right? You know what I mean? Okay, but cosine as well, I might as well write it. Cosine of x can be written as a complex exponential, e to the ix plus e to the negative ix divided by 2. Okay. All right, so these are really important. So you can transverse your integral from the reals to the complex domain, actually, when evaluating this. Okay. So you can use complex variables. It's a way of using complex variables in an interval. Okay, so that's one way to evaluate. Another way is, there's other methods too, but this is one way to evaluate it. Okay, hope you find that cool. Yeah. Yes. Well, you're going to learn a lot from me from my lectures. Yeah. There's a lot of math that is really handy that you haven't learned. Math is an infinite subject. There's so much to learn, it's not even funny, right? So, yeah. But yeah, I'm telling you, I have the mathematical toolkit that I know and that I can teach you guys and provide is endless. Well, not endless, but it's just too big. All right, so let's continue here. So sine x of this, cos is this. We're going to substitute that into this guy here. Okay, let's rewrite this again. So since I'm going to write over here, so because of the fact that, let me see, do I have enough room on this page? Yeah, I do, yes. Because capital S of x is equal to the integral, right? The integral from 0 to x of sine of pi t squared all over 2 with respect to t. Okay. So hint, hint, we're going to substitute complex exponentials in. Okay, so capital S of x, s as a function of x, is equal to the integral from 0 to x of sine pi t squared. Now just replace all x's with the pi t squared over 2, right? That's what you're doing here, right? You're inputting a function, a variable into the function. So this becomes a sine, let me just get rid of this, sine pi t squared over 2. That's going to be e to the I pi t squared over 2. So e to the I pi t squared all over 2 minus e to the negative I pi t squared all over 2, all divided by 2 with respect to t. Okay. Any questions? That was for sine. We're only using it for sine. The sine complex exponential we're using, the first one. Okay. Oh yeah, yes, that's right. Yeah, to Shido. See 2 listings on your website, but I like to get a paperback copy, so I want to make sure. Yeah. The paperback is yeah, that's available. Yeah. You can get that one. It depends which one you want. Yeah, they're both available. Yeah, there's the ebook and there's also the paperback. Okay. So yeah. Okay. All right. But yeah, there's both the ebook and the paperback for this book, Advanced Integration Techniques. Depends which one you want, whether you want a digital copy or a paperback. Some people prefer to have a tangible book, and it's probably better in my opinion. Or you can get the digital copy if you like have a iPad or whatever. You just like sliding and seeing the visual on your phone. Doesn't matter. All right. Okay. But continuing on, we've got this guy over here. Right? So s as a function of x is equal to integral from 0 to x of, I'm just going to split this up. You can just say that this is like saying 1/2 e to the I pi t squared all over 2 minus 1/2 e to the negative I pi t squared all over 2 with respect to t. Okay. Right, so that's what we've got here. The download icon meant I wanted to make sure. Yeah, that's what it is. Yep. And it works even better on desktop. I think on your phone it should work too, like you press the button, but desktop definitely works. Sometimes on phones and desktops, the same website doesn't operate the same. If you know how websites work, yeah, they're funny for sure. Yeah, but both should be fine with the click button. All right, so we've got this guy right here. So we're looking at the sine function, and now I'm going to FOIL in the integral operator. That's all I'm doing, right? So this is just going to be s, capital S as a function of x. I'm integrating from 0 to x of 1/2. 1/2 comes out, it's the constant, okay? It's the constant. E to the I pi t squared all over 2 with respect to t minus 1/2, and then I'm integrating again from 0 to x e to the I pi t squared all over 2 with respect to t. Okay. All right. So I hope that is good. All right. So this is what we've got so far. All right. So that's how our integral is breaking up. Okay. Now, there is a way to integrate this. If you look carefully. Okay. There's a way to integrate that. If you notice, it looks something of a Gaussian integral. I'll be right back, guys. I have to use the washroom. It's washroom time. I'll be right back. Yeah, 1 second. Yes, they're working. All right, guys. It's back from the bathroom. All right. Okay, so I just want to make sure that you guys are following this. Okay. So this is how we're going to look at this integral. Now, the next thing to deal with here is that we have an integral from 0 to x of e to the I pi t squared over 2 power. How can we deal with that integral? How can we deal with that? Also, Pseudo, let me know if everything's okay on your end when it comes to purchase. But yes, right now we're looking at this integral. So this guy right here, okay, what we should look at is doing some sort of a Gaussian manipulation. Okay, this would be a Gaussian, some sort of Gaussian manipulation here because this is e to the power of some constant times t squared, right? For those of you who don't know or don't remember, definition of a Gaussian integral, okay? Definition. As you can see, I always have to go back to the theory, but quite often when it comes to advanced math, yeah, I always have to go back to theory, right? Theory is everything, okay? So this integral right here would just be for a Gaussian. A Gaussian is defined as this, integral from minus infinity to infinity of e to the negative x squared dx is equal to root pi, okay? All right, so it's going to be like something of that nature, right? Now, that's for a Gaussian. Now, my question to you, are we using a Gaussian, a direct Gaussian substitution here, or do we need to use, what's it called, the error function, right? So definition of the error function, again, just to make sure you remember, error function as a function of x is equal to 2 over root pi, integrate from 0 to x, right, of e to the negative t squared dt. Which one do we need to use here for this first integral? Okay. Just let me know. Want your feedback, guys. Come on. What's integral we have to use? This definition or this definition to calculate this? How are we calculating this integral? Anybody know? How do we calculate this integral? Guess what? We're using the error function, right? Because we can see that we have an integral from 0 to x of e to the negative t squared dt. The only difference here is we have an integral from 0 to x of e to the I pi t squared power over 2 dt. We have to make some manipulations here, okay? So if that's the regular error function, 2 over root pi integral 0 to x of e to the negative t squared, we have to find it when it's e to the I pi t squared power, I pi t squared all over 2 power, right? And then manipulate it and solve for an error function of some sort. Okay, so let me go to the next page. Okay, so as I said, the error function, right? So I'm just going to move over here, right? So by definition, right? So by definition of the error function, right? We know that error function of x is equal to 2 over root pi, and then I integrate from 0 to x of e to the negative t squared dt. All right. Right, so this function right here, okay. Then the error function. Now we want to find the error function when we have e to the I pi t squared over 2 power. So this is going to be 2 over root pi. Integrate from 0 to x e to the negative I pi t squared power over 2 dt, right? Okay, we want to figure out how we can manipulate this. Now we want to solve for this guy. So if I'm solving for this, I need to multiply both sides by pi all over root pi over 2 to isolate for this. So this now becomes root pi over 2 times the error function of x is equal to the integral from 0 to x of e to the negative I pi t squared over 2 dt. Does that make sense? Okay, so that's what we've got right now. By the way, Shido, let me know if everything's okay when it comes to clicking on the icon. Okay, so this is what we've got so far. We got this error function multiplied by root pi over 2. And then we just substitute in, right? If that's what this is equal to, then if we go back to our problem that I located earlier, yeah, then we just substitute that in here, just multiply by 1/2. So s, capital S, the sine function as a function of x, right, is equal to 1/2 times, right, 1/2 times root pi over 2. So it's going to be s as a function of x. Capital S as a function of x is equal to, what was it? We said 1/2. Yeah, so 1/2 times, we said this was root pi over 2 times the error function of x. That's our first integral, okay? Okay, so that's our first integral. Take care of that. Minus 1/2, same process, minus 1/2, okay? So minus, let's put that here. So it's going to be minus, so minus 1/2, where's minus 1/2? Okay, that was e to the negative I pi t squared, right? Let me see, negative t squared. Yeah, so one was negative. Okay, so for the negative one, let me keep track here. That was for negative, so negative, negative. Okay, this is positive I pi t squared. Let me be careful here, because these were both positive. Oh yeah, one was positive, one was negative. Oh yeah, that's right. Yeah. So this is negative e to the negative I pi t squared. So by definition of the error function, that's going to be for the second one. Okay, so it's 1 second. The second one is this, the second part here. So this should have been the -1/2. Let me move that over. So what we did was we dealt with the second integral. So -1/2 root pi over 2 times the error function as a function of x. Okay, the first part we don't know. Okay. Okay, no problem. Yeah, PayPal does that. Yeah. You always have to PayPal away. Yep. But yeah, you just have to fill in the PayPal stuff. All right. So we're looking at, so the second part is what we've got here, right? This integral. Okay, so -1/2 root pi over 2 times the error function of x. Okay, so we've got that. Now, I have that integral because, once again, I just want to make sure if anyone's coming in or people who are not understanding, right? Once again, the reason for that, okay, just 1 second. Let me see if I can find it. Where was the definition? Yeah, this 1 sec. Yeah, this part here. This is negative. This e to negative I pi t squared over 2 power is the error function, right? Because the error function is the 2 over root pi integral from 0 to x of e to negative t squared dt. We can see that this portion here is the error function. Highlighting error function. So we can replace that with the error function. And I have to rearrange that integral by multiplying both sides by root pi over 2 times the error function to get that in. Okay, so we have the second part of the integral, not the first part, if that makes sense. Okay, so the second part we have, the first part we don't have. Okay, so that first part here is what we have to deal with. Okay, that first part. Okay, so what is that first part? So this part here, e to the I pi t squared over 2. Okay. Now, there is a way to deal with that. You can do the long way or the short way. Okay, I'm going to get to that in a second. Yeah, the shipping is worldwide. It doesn't matter. The shipping is worldwide. Yeah, shipping is worldwide. Yeah. Yes, that's not a problem, though. Shipping's worldwide. So I hope that answers your question. Comes from England, but yeah, it's worldwide. So yeah, all shipping for paperbacks are worldwide. Okay. So I hope that helps. Helps to answer your question. Worldwide. All right, so we've got this guy here. All right, so we have our error function for the right part. So again, guys, worldwide for the paperback is worldwide. Okay, so if you're interested in the book, paperback worldwide. Okay. Okay. So let's get back to it. So yes, you've got this part here. 5. So we were looking at this integral here, right? So we got the second part of our integral. Okay, second part we've already done. The first part, we don't know what it is because we don't have a definition for the first part of our integral, if you know what I mean. Like, if you look over here, the Gaussian is e to the negative x squared. It has to be written in terms of e to the negative x squared power, right? The error function has to be written in e to the negative x squared, or t squared, doesn't matter, e to the negative something squared power. So we don't have, for the first integral, a way that we can use a representation to solve it, if that makes sense. You guys following? Right? So we don't have a way to solve it by standard definition right away. So again, pseudo, yes, we ship to California. That's not a problem. Right? Shipping is to California. Anywhere on the planet. It's global. Okay. Right. Okay. So we've got all of this. So we have our second integral taken care of. Right. Now our first integral, what we may need to do, what I'm thinking, because I haven't tried this. I haven't tried it yet. We can use because we cannot use U substitution, right? That's what I'm saying. If we use U substitution, we have a disaster. Okay. Actually, no, we can use a Gaussian integral. If we change it again, it should still work. Not Gaussian integral. An error function of some sort. No, because we would have to see Gaussian would work because convert the polar, then it would be r squared, and then be r d theta to get the double polar coordinates. For those of you who know multivariable calculus, you know what I mean. Double polar coordinates. That won't be quite it here because we don't have doesn't work because we're integrating from 0 to x. Double polar coordinate transformations for a Gaussian integral has to have improper integrals here, improper integrals, right? So that's not going to work. So here's your homework question. I have to think about it myself. We already figured out the second part. Okay. We already figured out the second part. Just 1 second. We figured out what this was. This was some constant multiplied by the error function. Try to figure out the first part for homework. Once you get the first part and the second part, then you found capital S as a function of x. Okay? Right, so try to figure out what this guy is. Okay, try and figure out what that guy is. Right? Oh, really? That's bizarre. When you pressed on it. Right, okay. That's weird. I'm gonna have to look into that. That's bizarre. You should be saying it's not available on your reason. Give me a sec. Give me a sec. Let me see here. See here's something. Articles box. Just give me a second. Let me see here. Okay, let me see. Just add to cart. Add to cart. Let me see what's going on. Email to, let's say I just used, all right, let's change the country. United States. Always remember the United States is PQRS TU, United. Just 1 second. Just going to try and fix it right here. See if it's going to. State. Let's say we just use California. 1 second, California. Oh, I think now when you put your if you put California, it might do the same as it did for me. That's really bizarre. That's a bit bizarre. Just see here, California. Is the issue coming here or on the next page when you're doing it? Like, is it on this page or the next page when you go to the checkout? Just let me know. Because you go into, that's why I put my address and go to the next page, tells me the region error. So the next page for checkout. Okay. Somehow that's what it is. Okay, let me see here. I'm just going to make something up. I don't know if it's going to, let me see when I press continue, let's say use 3 or whatever. Let me just see what happens. Are not currently available. Yeah, that's weird. Okay. There seems to be an error right now. I have to look into that. You can get the ebook then. Okay. Try getting the ebook. Yeah, because the ebook is going to work for everything. For some reason, it's not working for California right now. I still have to edit that. But thanks for letting me know. But yeah, you may have to get the ebook. Okay. Seems to be acting weird. Yeah, it seems to be acting weird because it should be doing it for California. It should be working. But yeah, the ebook. Yeah. Yeah. So just check the ebook then. Yeah, because it's acting weird. I have to check with my supplier. Okay, yeah, go ahead. I have to check with my supplier that does print on demand for physical copies of why it's acting that way. All right, let me know how it goes. All right, so for homework, for the rest of you guys, this is going to be for homework. So figure out what that question is. Okay. So what's that question? So I hope you guys write it down. All right. The question minus 1/2 root pi over 2 error function. So we're going to figure out, oh, hint, by the way, this integral, as I mentioned, that we don't know what it is, e to the I pi t squared dt, okay? Try using, here's a hint for homework. This guy here, try using Euler's identity. Euler's identity states that e to the I theta equals cosine theta plus I sine theta. Right? I use this, right? So that's the hint in order to integrate that, because we can't integrate that because both the error function and the Gaussian integral don't have both have e to the negative of e to the negative power squared of something, of some variable. Here's e to the positive power squared. Okay. All right. So I hope that made sense. Okay. And then finally, the last problem, which will be for homework, is I want you guys to study the behavior of an exponential integral. Okay. And when I mean study the behavior, I mean look at the exponential as a function of x as x goes to 0. Okay. So I don't mean necessarily, I mean, you can try to integrate it, but I mainly mean like, yeah, you can do that, but also study other things too, the modeling behavior, the asymptotic behavior, the whatever else, you know what I mean? Okay, so not just algebraically evaluate it, but geometrically try to see if you can understand graphically the model. Okay, right, so I hope that made sense. How's it going, Shido? So let me know once you've gotten through, Shido. Go to articles and books, just for anyone to know. If you want the ebook or the paperback, let's go to ebook. Right? So just 1 second. Ebook, add to cart, and so forth, right? Okay, so get that. And go to checkout, right? Just go to checkout here, right? And then just put a payment and place order and pay. That's what you would do here. Okay. Just helping anyone who wants to get the book, Advanced Integration Techniques. Okay. So again, you would go here, go to Articles and Books, click on the ebook copy. If you want the ebook, press Add to Cart. It's more direct, and this would be working that way. Okay. Just want to make sure everyone's there. Just another internet guy, you still there? So let me know. Hope you're enjoying the live show. Name for billing, since I used my ANS card, but hopefully it works just fine. If not, I'll try again in a few minutes. Okay, Shudo, good. Good. Excellent. So I hope you enjoy it. It's interesting how I've partitioned it. Call and do a whole bunch of nonsense. Okay. Is it going well? Did you find a payment method that will work? Did you find a payment method that worked? Let me know if everything is going well. Should have. Because yeah, it should have went. All right, guys. At the same time, again for homework, the research problem number 3. I want you to study the behavior of the exponential integral. So our exponential integral is bounded from minus x to infinity of e to the negative t dt all over t. Okay, so exponential integral is from minus x to infinity of e to the negative t dt all over t. Okay, so those are the 3 problems for homework. So that's the 3rd problem. The 2nd problem, I gave you a hint. This guy here can be replaced with Euler's identity, cos theta plus I sin theta. Just replace the theta with the pi t squared, and you can figure out how to do that. Okay. By the way, inside here, what you'll find interesting, if this is pi t squared and pi t squared, is that you can replace those. Again, it's inside of what's it called? A complex integral inside of a sine and cosine Fresnel integral, which gets pretty interesting. Okay. Yay. Perfect. Okay, so you're saying it went through. Okay. All right. I'm glad to hear that, sir. All right, so take your time through it. I recommend what's it called? Going through the theory first. Okay, the theory is very important. Okay. Yes, I got the payment. Thank you, Shudo. So go through the theory first. I've partitioned it interestingly, right? Like table of contents, stuff like that, and everything else. But go through the theory first before doing the problems. I strongly recommend it. If you have a solid understanding of the theory, the problems will make more sense. Otherwise, since they can get more complicated, it's going to look alien. But if you understand the theory in depth, you're going to understand everything else. Okay, so understand the theory, right? The theory is very important in the book. Okay, I hope that helps you though. And I have the theory for all 43, so 42 chapters, yeah, 42 chapters. How many pages? I think it's like 400 pages, around 400 pages or something. All right, so I hope that helps you though. Okay. All right. Okay, that's it for today, guys. Now tomorrow I'll have to tune in more often to keep up. Yes, please do. Please do. Yes, yes. There's going to be. I'm going to tell you what my schedule is. It's what's the schedule again? Because I'm ending this live show right now. I'm just about done. I'm tired, but stay tuned. There's going to be plenty of interesting concepts coming up. So Wednesdays at 8:30 p.m. Eastern. That was my time. I know for you, Shudo, that would have to be 5:30 p.m. Because California time is 3 hours back. So for you, it would be 5:30 p.m. on Wednesdays, right? But anyways, Wednesday at 8:30 p.m. Eastern time, comes in the Eastern time zone. Thursday, 7 p.m. Eastern time. Now Thursdays is not a live show; it's a stream. Okay, so Wednesday 8:30 p.m. Eastern. Okay, is always Wednesday 8:30 p.m. Eastern is always the live show. Thursday is just a regular stream. Okay, 7 p.m. I'll post something interesting, a nice video continuing from the either the book or some other concepts related. Yeah, Thursday will be 7 p.m. Eastern, not a live show. And then finally on Sunday is another stream. Okay, so stream on Sunday at 7:30 p.m. Okay. Perfect. So if you wanna stay tuned for the live shows, it's always Wednesday. Okay, so Wednesdays are the live shows. Thursday and Friday are streams. So it depends what you find better to help you, right? If you like the live streams, come Wednesday. If you prefer, just the regular stream, come Thursday and Friday. Yeah, exactly. That's the whole point, right? Well, I thought when I was writing the book and in general, the whole point of it was to make sure I'm talking about new stuff, right? I know, like, still based on concepts that you already know in university, but why talk about standard cases? Why talk about only standard cases that are simple that you've already known if it's, if you've already done that? The point is to stretch your abilities, okay? Because you need that in university and to continue on afterwards. Okay, all right. Yes, that's exactly why the theory is so important. Yes. All right. Thank you, Shudo. Thanks for making the purchase. Again, for those of you, and stay tuned. Again, Wednesdays at 8:30 is the live show. Okay. And for everyone else, stay tuned. There'll be plenty more of interesting concepts on advanced integration techniques from my book, and also not just math, but also physics as well. Interesting concepts as well. I will go back at some point to look at those too, but for now, we're looking at my new book, Advanced Integration Techniques, which you can purchase on my website. If you want to learn to think in an abstract mathematical way, especially for calculus, that's the book. And or if you're also looking for tutoring, I'm also a tutor, right? If you're looking for tutoring and you want to learn how to think geometrically about calculus or linear algebra, I'm always available for tutoring. You can DM me on the links below. Okay, it'll be mentioned in the chat. Have a good night, guys. Well, it's nighttime for me. I don't know you guys, but have a good day, and I'll see you next time. All right. Plenty of more math coming up in the next live streams and streams. Let's make math great again. Okay. Have a good day. All right. Bye-bye.